The James Webb Space Telescope has made history by discovering the earliest black hole known in the universe. This infrared observatory found a massive black hole that existed when the universe was only 470 million years old, roughly 3% of its current age. The discovery became even more intriguing when scientists measured the black hole's mass, which turned out to be 40 million times that of our Sun. This is 10 times the mass of Sagittarius A star, the supermassive black hole located at the center of our galaxy. This finding appears to have resolved one of the most significant mysteries in astronomy, the origin of the first black holes in the universe. But how did such a massive black hole form so quickly in the baby universe? What's so puzzling about the mass of this supermassive black hole lying at the edge of time? Finally, and most importantly, how does this discovery shed light on the birth of the first black holes in the cosmos? The origin of supermassive black holes has been a challenging question for astronomers. Two models have been proposed to explain their origin. The first possibility is that these black holes result from the collapse of the first stars, known as light seeds. However, there's a timeline issue with this theory. According to evolutionary models, the first stars formed approximately 150 million years after the Big Bang. These early stars were likely quite massive due to the conditions of the early universe, allowing around 50 million years for these stars to evolve and reach the final stages of their life cycles. Light seeds would form roughly 200 million years after the Big Bang. However, it would likely take several billion years for these light seeds to accumulate enough matter from their surroundings and grow into supermassive black holes. So the discovery of supermassive black holes by the James Webb Space Telescope in the first 500 to 700 million years post-Big Bang questions the validity of the light seed model. Could it be possible that the first black holes rapidly accumulated a vast amount of matter, quickly transforming into gigantic black holes? The answer is no, due to a limit known as the Eddington limit. Accretion occurs when the intense gravity of a compact object draws material from a star towards its core. Due to the conservation of angular momentum, this material doesn't fall directly into the core, but instead forms an accretion disk around the object. As material accumulates on the disk, gravitational potential energy is released, leading to the emission of thermal radiation, often in the form of X-rays for black holes. However, as this radiation pushes outward, it can reach a point where it becomes strong enough to blow away the surrounding matter, halting the black hole's further growth. When radiation pressure surpasses gravity, accretion stops, putting a limit on brightness. This leads us to the second possibility for the origin of supermassive black holes, the direct collapse of massive gas clouds into black holes, known as heavy seeds. These gas clouds are initially quite huge, allowing them to potentially evolve into enormous black holes within the required time frame. However, the challenge was the lack of concrete evidence supporting this theory of black hole formation. This is where Webb's data comes into the picture. To solve the mystery of the earliest black holes, the James Webb Space Telescope joined hands with the Chandra X-ray Telescope, designed to detect X-ray emissions from high-temperature regions of the universe, such as the accretion disks of black holes. The most exciting part of this discovery is understanding how we are able to see the black hole. For that, scientists utilized the magnifying power of cluster Abell 2744, located about 3.5 billion light-years from us. This phenomenon, known as gravitational lensing, occurs when the immense gravity of massive foreground objects bends or deflects the light from objects in the background. While this can distort the images of these background sources, it also magnifies them, making it possible to observe distant objects in greater detail. Telescopes like Hubble and Webb use this natural magnification to study objects that would otherwise remain hidden. Returning to the discovery, a massive galaxy cluster acted as a gravitational lens, magnifying the galaxy containing the massive black hole by a factor of 4. Initially, when astronomers observed this gravitational lensed galaxy in a Chandra X-ray image, They were uncertain about its nature. They investigated 11 similar gravitationally lensed galaxies detected by Webb and identified an X-ray source that matched their target in terms of position and X-ray spectral characteristics. This X-ray source, amplified by the cluster lens Abell 2744, was eventually identified as belonging to the galaxy UHZ1. These X-ray images from the Chandra telescope played a crucial role in identifying and studying the gravitationally lensed UHZ1. The first image showcases the massive cluster lens, Abell 2744, with a small square box highlighting the location of UHZ1, which harbors the massive black hole. The next image reveals the extent of X-ray emissions from the galaxy and its vicinity. In this image, a pale yellow indicates high X-ray counts, while black represents the lowest counts. The central region, where UHZ1 is situated, showed the most intense X-ray emission. After analyzing the X-ray spectral properties of the accreting black hole at the center of UHZ1, astronomers estimated the black hole's mass to be around 40 million times that of the Sun. But things took an interesting turn when they calculated the galaxy's stellar mass by analyzing its starlight emissions. That number came out to be roughly the same as the black hole mass. This contrasts sharply with the observations in the local universe. For example, the black hole at the center of the Milky Way constitutes less than 0.1% of the Milky Way's stellar mass. This was the first time astronomers discovered a galaxy whose stellar mass and black hole's mass were comparable. The only thing now left to find out was how this supermassive black hole possibly formed in the first place. To determine whether the black hole in UHZ1 originated from a light seed or a heavy seed, scientists developed two models and conducted simulations to observe how these seeds would evolve if they originated around 150 million years after the Big Bang. The key question was whether they could attain the estimated mass by the time the universe was about 500 million years old. In the first model, a light seed arising from the remnants of the first stars began with an initial mass of 10 to 100 solar masses. It evolved by accreting matter at a rate consistent with the Eddington limit. However, the simulation showed that such a light seed would fail to reach the estimated mass of around 100 million solar masses. Conversely, the second model involved a heavy seed starting with an initial mass between 10,000 and 100,000 solar masses. With consistent accretion at the Eddington rate, this model successfully reached the required mass estimate. Additionally, scientists explored a third scenario where a light seed accretes matter at more than twice the Eddington rate. This model would necessitate an enormous amount of matter being fed to the black hole over an extended period of about 300 million years. However, this scenario is considered highly improbable, as it requires a sustained supply of gas to the black hole even after the matter has lost all angular momentum. This situation is unlikely, given the dynamics of such systems. There are 4 reasons why this study is important. Firstly, it supports the heavy seed theory, suggesting that such early massive black holes originate from the direct collapse of vast gas clouds. Secondly, the galaxy hosting this black hole presents a unique case where its stellar mass is approximately equal to the mass of its black hole. This categorizes it as the first ever outsized black hole galaxy, or an OBHG, a rare phase in galaxy evolution where a heavy seed is present. This phase lasts until a transition occurs, flipping the mass ratios to those comparable to the local universe. Third, the study highlights the importance of gravitational lensing yet again. Gravitational lensing has enabled us to discover this unique black hole and even Earendel, the most distant single star identified to date. Lastly, considering the universe's age of about 13.8 billion years, the identification of a black hole in UHZ1 dating back to when the universe was only 470 million years old positions it as the earliest black hole ever discovered. Before wrapping up this video, I want you to think about something. How often have you wondered about the stars, the vastness of space, and our place in this universe? It's fascinating, right? But where do you start if you want to understand it truly? That's where this video's sponsor, Brilliant, comes in. Brilliant is the best way to learn math, physics, astronomy, data science, and computer science interactively. All you need to do is set your course, and Brilliant will design a perfect learning path for you. Their interactive approach lets you pick your path and pace, making learning feel like a personal journey through the cosmos. And the best part? It's not just about watching and listening. You're actually solving problems that stump the world's best minds. Their astrophysics course, for instance, is a gem. It's crafted to transform you from a curious observer to someone who truly understands concepts like black holes, dark energy, time travel, and the physics that govern our universe. And if you ever get stuck, Brilliant's explanations are like having a friendly expert right beside you. So here's the deal. I've arranged a special offer for you with Brilliant. To explore everything they have to offer for free for 30 days, visit brilliant.org/the secrets of the universe, or just click the link in the description. And for the first 200 people who sign up through our link, you'll get an exclusive 20% off on the annual premium subscription. So thanks to Brilliant for sponsoring this video, and thanks to you for watching.